So how do I simulate these observations? So I need a sample size, right? Okay. So I may start with, let's say, 10 observations. Then the mean is what? 10. Is that okay? What is the variance? So standard deviation, I said if the variance is 2, then in R you have to give it SD. So SD will be what? Square root of what? 2. SQRT. Oh, yeah, SQRT 2. Is that okay? All right. So I can generate my observations. And this is mine. You can check yours as well. It will be different. We can get a histogram of it. So does it look like a normal distribution somehow? Okay, like that. Okay. So yeah, this is how it is. Okay. Now, the question is, I need these estimators, right? Okay, so what I can do is to find them. I can write a function, a small function to compute them, right? Okay, so let's say we will say mom MLE. It's a function. You can, I mean, it depends on you. So it takes in a data X, and then the moment estimator is just what? Variance of S. Is that okay? Is that okay? The variance of S is just the moment estimator. But the MLE, what do we need to do? Remember, we found out as what? N minus 1 divided by n times what? S squared. Is everybody okay? So we need to write that as what? N into bracket n minus, no, we haven't found n. So n will be what? Length, yeah. Length of X. So we'll have n minus 1. Then we divide by what? N, right? We can put all that in brackets and multiply it by what? var of X. Is everybody following? So we get MLE, we get what? The moment estimator as well. Is everybody okay? Good, okay. So now we can return this. So the estimate is just what? C mom and then MLE. Okay. And then I return this. Okay. So this is our function. So as I said, in our functions, if you know how to write functions, I mean, you are good to go. Okay? So please take this. So I've done mine. I can now call this function to calculate the sample variance for the sample I generated. So you see each of them computed the variance, but there are differences, right? Okay. Here I can go back and name them so that when it pops up, I'll get the names. So there we have it. Is everybody okay with this? So it's a simple function. It calculates the length, which is the sample size. It finds the variance. Remember, the variance is what? The moment estimator. Then the MLE. We need to multiply it by that coefficient to get it. Then I name the vector, and then I return it as a vector. Is everybody okay with this? Please, are you okay? Any question? Okay. So please run it with the sample you generated. And what I'm going to do is to go and re-sample again, and then come and compute. You see, each time I do it, I'm going to get different values. Okay? Because there is random sampling. Okay. But the key thing is that we see that the moment estimator is producing better results than what? The MLE. Because we are estimating 2, isn't it? Yeah. Okay. So, but just 1 is not enough in statistics to conclude that 1 is better, right? So we can repeat this over a length of time, usually over 800 or more, and then we can compute the mean, okay, and then we subtract the parameter from it, we get a bias. And then we can find our mean square error as well, quite easily. Okay. So what I'm going to do is that, so I'm going to generate several samples. So how do I do that? Well, so many ways. Okay. But I can use this. So I can use S-apply, which is the apply family of functions. There are several ways you can do this. I ask you that you should check. There's a short video on this, on the apply family of functions, because they come in handy when you are doing something like this. Okay. So I can say I want 1,000. So it means that I want to generate 1,000 random samples. Okay. All right. Then function I. So in other words, take each of them. I'll just say I'll know. N is equal to, so here, if I'm starting, I'll start N is equal to, let's say, 10. Mu is what? 10, right? And then sigma squared is what? 2. Okay. So there I can then put in that N is equal to N. Mean is equal to what? Mu. And then SD is equal to what? Sigma. Why am I doing this? Because later on we'll change the sample size. Or you can change the sigma and then the mean. So we are not going to the function to now go and change anything. Once we change the data at the top, we can just run it. If you don't do it like that, it means each time you want to run it, you need to go in and change something. So that's why. So the SD is what? Square root of what? Sigma. Or sigma squared. So that's how I'll do this. Okay. So now let's see. 1,000 will be too much. Let me just generate 5 just for us to check before we move on. Okay. So this one is now a matrix if I go to environment. this is what M-SAMP, right? So you see M-SAMP is a matrix made up of what? 10 rows and what? It will be 5 columns. You see? So the rows are what? The rows are what? And the columns are what? So we have 5 samples. Each of them have what? A sample size of 10. Do you remember? That n is equal to 10. So that's the sample size. We can transpose it if you want your samples to be on the rows. Is that okay? Okay. So that's it with this, and I can display it. So there it is. First sample, second sample, and so forth. Okay. Are you okay? Please, are you okay? Can we move on? Can we move on? You need to stop me if you don't understand anything. I'll ask you this in the exam. Not this, right? But you implement a simulation study, so it is in your own interest to, because I don't want to see you in this class again. Yes. Yes, so as I said, this one, what it's saying is that take the first one, so I will be 1, but I usually don't use I. In some cases, you may use it as well. So what we are saying is that repeat this. Okay, we can also use rep, I think rep to do it. There are several ways you can do this. But I wanted to create a matrix of data sets. So what it says is that just generate this. How many times? 5 times. So when you want to do it big, you change 5 to, let's say, 1,000. So in other words, I can also do this. So R is usually the number of repetitions. So I did 5. So it means here I'll just do R. So that I don't go and change anything in the function itself. Okay. So let me do it again. If I do it, I check, I'll get different samples. That's all. So this is a sample. Let me display it again. So this is my sample, the generated samples. So you see the columns are the samples, right? And the rows are the observations from each of these samples. Please, have you been able to reach here? Not yet. What is the problem? If you're having problems, please let us see. Your function is like this. Have you gotten it? Please, have you gotten it? Are you okay with the function? You need to respond so that I know whether to move on, do something else. Please, are we all okay? Can we move on with the function? Okay. So after the function, we tried the function on our sample, right? And it was able to generate what? The moment estimator, the maximum likelihood estimator. However, we want to find bias and what? MSE, to know which one is better, right? Now, to do that, I cannot just compute just one observation and subtract it from the parameter and tell you that this is a bias. Okay. Remember the shooting example that I gave over there. There must be several shots. Then we can now calculate how well you miss the target or how well you get to the target. That's the bias. Then we can measure variation. So that's what we are trying to do. So it means that I need to generate samples, right? And there are several ways you can do this. I've just used one way using the supply function. Okay. So to do that, we need the number of sample, and mu is this. This one I can change it to even 0, right? Which means the mean for the normal distribution is what? 0. Okay. I can change it to 100 if I want anything. Okay. Here I can change it to, let's say, 20, maybe 16, which means the standard deviation is what? It's 4. Okay. All right. So let's deal with this. 10 and 100. So these are my observations, each of them. And when you check it, they are not the same. Each sample like this is not the same because these are random generations. And we call this Monte Carlo methods, right? Or Monte Carlo simulation. Okay. Now, so let's see. So what I want to do now is that for each sample, I want to compute what? The variances for each of them. Which means I have to take each column and compute what? The maximum likelihood estimate and what? The moment estimate. Is that okay? All right. Okay. So here we will say compute the estimates using the function. The function was what? MOM-MLE. Okay. Now how do I do this? Well, because this is a matrix, I can also use what we call the apply family. So here I give it a rectangular data. Then there is a margin. If the margin is 1, it's for rows. If the margin is 2, it's for what? Columns. So in this case, I have columns. Okay, then I need function. The function that I'm applying is just this, MLE. It's MOM-MLE. Okay, so I can do that like this. So this should be, okay, yeah, like this. There we go. So once I do this, you see, it's each sample, we had 5 samples, right? The variance through the MLE, through the method and moment is calculated for each of them. So the first column is the first what? Sample. Remember, I changed my parameters to this, right? Okay, I can go back and change it. I think I was using it. At first, we were using 10 and 2, yeah. So maybe we should revert to it so that people do not get confused. Okay, so I can rerun this. Okay. What is the parameter? What is the parameter here? The true value is what? It's 2, isn't it? Okay. But you see, sometimes they are going way over it. Okay. All right. So now if I take one row, I can now find the mean and subtract the parameter from it. That will give me the bias. Is everybody okay? Now, then I can also find each of them. Okay, I can subtract the parameter from it and square it and divide by. That gives me what? The MSE. Because the MSE is just what? The variance of what? The MSE, of course, is the more or less like the variance. If it's unbiased, it's the variance. And so, but in simulation study, we find the MSE as is. So the number of time I repeat, remember the bias is just the expectation. So the bias is equal to the bias of theta cap will be equal to the expected value of theta cap minus theta. Now here, how do you find the mean? We can only find average. So in now we are going to find mean of all the estimates. Then we subtract the parameter from it too. Is that okay? Now to get the MSC, I need to also do this. So the MSC of theta cap will be equal to the number of runs that I made, which is in this case 5, right? Okay. Then I need to sum the theta I minus all, theta all squared. Is that okay? So that will give me my MSC. Remember, I can now put in the average of the theta caps, and then if I expand it, I'll get bias and what? Variance. Why? Because that's the number of estimates that I have. Is that okay? So in this case, we have like 5, right? But yeah, repetitions, yes. Because the t-test will be, of course, the I sigma will be I from 1 to what? R. Yeah, so that's it. Okay. So let's see. It means that we need to write a function for each of them. If you like, you can also do it in like together so that you can calculate the bias, you can calculate all the mean square error. Okay. So let's say bias MSC is also a function. So such a function, how can I compute the bias? What do I need? So I'm writing a function for the bias, which means I have arguments. What arguments am I going to put in? The parameter and what? And the estimates. Is that okay? So you need the estimates you have found. In this case, our variances. And then what? The parameter value. Okay. So how do we do that? Well, we will say the EST and what? And par, which is a parameter. And par is a function, so maybe I'll just do this. Okay. So now bias, how do I compute the bias? It will just be the mean of what? The estimates, or let me just use theta hat, theta dot hat, so that it will be easier for people to know that this is theta. Minus what? Then here I can do theta. So theta is a parameter, right? Is that okay? So this gives us bias. Is everybody okay? Please, are you okay? Yes. That will compute the bias as we find it. Okay, then we need the MSC. How do we compute the MSC? Well, we need to find, let's say, the mean, because I'm dividing by R, so I can use the mean function, right? Is everybody okay? This one is just the mean of what? Sigma minus the theta hat minus theta all squared. Remember, the theta hat will be a vector. That is of length what? R. Okay, so we can use mean. So at this time, I must also say that, I mean, as you move on, when you do masters and so forth, you realize that, or we know that the mean is affected by what? Outliers, right? So in some cases, especially in my research area, MSC is not always the best thing, because I can just get, because I deal with extreme values, I can just get one and then it will inflate this MSC. It becomes difficult for you to even get graphs to, because just one outlier can overstretch your graph, okay, such that all of them looks like they are zero, with the exception of that one. Okay, so MSC is always not the best. So in some cases, you report on MSC or the relative to a standard. Okay, that's the relative efficiency that we can do. So if I know that the maximum likelihood is the benchmark, then I can express each other estimator as a fraction of what? The MSE. Right? So that I can determine that if it is smaller, then it's better. Or if it is, so I can express it even in percentage. That's another way to do it. Yeah. Okay. Well, so this one will be mean of what? This, but we need to square all of them, right? And that gives us the MSE. So we square this. Please, are you okay? So that's it. Okay. So now I can return. We need to name it. So tab. Or maybe let's use a data frame. What do I? Okay, so maybe tab. And then we use a data frame so that it will just name it for us. So bias. And then MSE. Bias and MSE. And then I return what? Tab. Please, are you following? Yes. Then, oh, because mean you sum. Yeah. So the mean will sum everything you pass in. But what we are passing in is what? The sum of squared deviations. Sorry, the deviations squared. So it will take it as when we write something like this, it is in your interest when you go home to sit there and run it line by line, which means you need to assign theta dot hat and then theta, then you run a line by line and see what is happening. Yeah, that's how you learn. Okay. So when we finish this, your task will be to put all this together such that when you run it, it will generate observations, calculate it, and give you bias, then you make a decision. Okay. So if you're able to do that, then, you know, here we have high-performance computers over there. Okay. So let's say if you are doing your project and you are doing some of these simulations. In my case, I mean, I could put a laptop on, then it would take like 3 months or 6 months for it to run for you to get a result. Okay. So usually I write, during my PhD, I write the programs here, I send it to the HPC when I come on vacation in Stellenbosch, and then it will be done, and then when I'm here, I can just go. And we've implemented some here. So once you get any DEX on your this, and we give you the code, you can, so you open R, but you are operating it on that computer, not your own, right? So everything is like, it gives you a virtual desktop, and then you can send your work, and then everything comes to you. So if you're able to write it that way, you don't need to interact with the program. All you have to do is send it to the program. It does it. Once it is finished, you can then go in and get your results. The one that we use in Stellenbosch, I mean, an email will come once the process ends, and then you know that it took, let's say, 3 days to do it. Especially those in phases and, oh. So I think he was not running any desk for me. Okay, let's move on. Okay, so it's quite an interesting thing if you understand some of these things. And especially those who do masters, you will do some of this. Yes. 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 Yes, we can use the bias squared times the variance as well. In that case, I would have just found variance of theta hat, theta dot hat, and then plus the bias squared. That's also possible. You get the same. You get the same thing. Okay, all right. So let's move on. Let's try whether this will work. So now we have this. Remember, then it means this one, I will have to say this out. Parameter estimates. Oh, was that? Yes, those are the parameter estimates, right? Good, okay. So something like that. So this will also be a a matrix with 2 rows and all 5 columns. So now I can use the same apply, but now I'm calculating the function should be on each row, no columns, because we are taking in the parameters from the moment, estimate from the moment, we pass it through our function, then we calculate bias and all, and the MSC. Okay, so let's see. So what I mean is that now I'm going to do the same. Now compute the bias. So bias stroke MSC for each row. So to do that, what do? We will call the same. We will call the same function and change it. So this one will be the estimates. Then I'm not going to use 2, but now what? 1, because I'm going to take it row wise, right? This one is actually margin. It's big margin like this. So when the margin is 1 is for row. When the margin is 2 is for what? Columns. What am I going to put there? This will have problems. I need to do a function because this one can only, it needs to take theta and what? And theta hat. Yeah. So over here, now our function should take, let's say, x. Then I will call bias mat, and then theta hat is now s, because the first row, let me come down, theta hat is equal to x, and then the next one, theta, should be equal to, do you remember what we used? So I don't like, is a sigma or squared? Is everybody okay? That's our parameter. Sigma squared. So theta is sigma squared. Let me try. Sometimes it works, sometimes. There we go. Okay. So, but it's unable to give us a, I wanted it to be in a tabular form. So if I want it to be in a tabular form, I need to write a function, calculate it, and be able to do it. So when we take the moment estimator, the bias is 0.15, a bit of overestimation. The MSC is what? 2.62. MLE. Hey, let me. Okay, so that's it. MLE negative 0.007. So which one is better? The MLE, yeah. Because the MSC is closer to 0 than what? That of the mom. And then if you take the bias in absolute sense, the MLE is what? Better. Okay. Is that what you got? Or you are here to? Remember, this is too small. I can't use this to, I need to go back and change this one to like 1,000 so that it generates several observations, right? N can be 1,000 because I was using this too. So the parameter estimates, now there it is. And still MLE That's a bit better, right? If we increase the sample size, oh, sorry. No. Okay, so the sample size is huge, which is good. It's the repetitions that I want to repeat. So sample size 10. Let me the number of repetitions to 1,000 and see what will happen. We have a small sample size 10. So this is what should be expected. Yeah, and you can run it over and over and over. You'll see a pattern. For smaller sample size, we expect the moment estimator to do well, in theory. But for larger sample size, we expect the MLE to do better. Any question? Okay. Oh, no, we are doing it for him, so he shouldn't worry. Tell me that I'll come there with a script, a form for him to fill. And the student does not need to be here. I think he can call me. I will explain it to him. I'll finish in like 20 minutes. Okay, please, have you been able to do it? Okay, so this is it. Why? Okay. Okay, so instead of a data frame, let me use a vector so that we'll get it in a data. We'll get it, it makes the comparison easier. So I'll go back here and change it to C instead of the data frame. Then when I do this, then it becomes easier. But still, I need to now name the row so that the first one, you know that it is for what? Buyers, and then the second row is for what? MSC, yeah, which is what I have not done. What do I have to do here? I can do it here. What I need to do is to include names. So the names of the tab is the same as the same thing, but of course in what? As so that it will appear. So you need to okay. So then I have to rerun it and do yeah. So it makes it easier for you to make a decision. Okay. And you can redo this over and over again by changing the sample size. So here you can check for empirical consistency. Remember, I'm using a sample size of 10. So if I change it to 20, you can check what the MSC, what are the values of what the MSC as you increase the sample size. Let's go back and change some of the parameters. So n is 10. I can even use 5 and see what will happen. So I do this. I don't need to write this. I need to comment on this. The function to compute buyers and what? MSC. Okay, so I can then do this. There it is. Okay. So there are, in some cases, one does better on buyers, the other does better on. But if I increase the sample size to, let's say, 500, that's a large sample size. What do you expect? What do you expect? If the sample size is large, what do you expect? The what? The standard error will reduce. So in order, the MSE will reduce. What do you expect to be the performance of the MLE and the MOM? Which one do you think will be the best? The MLE, yeah. So let's see what happens. Yeah. Not necessarily the case. Oh, it is, yeah. In terms of bias, yeah, good. In terms of MSE, also slightly better. And so forth. So this is what you were doing over there in 333. The challenge now is to know, so please when you go, take your time, go through the apply functions. It's very important because it helps you to maneuver. I can do this in another way. Just a moment. Hello, bro. I don't know how long it takes, but if I'll bring it to you now, then you fail it. Then we'll dispatch it to the dean. Okay. Yes, so we'll print it and add it. Okay. Okay. Please, any question? Any question? Otherwise, I'll leave you now. Okay, so I will send you this.